This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Good evening and welcome. My name is Nigella Hilgarth and I'm the Executive Director of the Birch Aquarium at Scripps. And I'm delighted to see you all here tonight for the latest Jeffrey B. Graham Perspectives on Ocean Science speaker series. And it's my great pleasure this evening to introduce our speaker, Dr. Cathy Constable. Dr. Constable is a professor of geophysics in the Cecil H. and Ida M. Green Institute of Geophysics and Planetary Physics. That's since September 2009. She serves as the Deputy Director for Research and Associate Vice Chancellor for Marine Sciences here at Scripps Institution of Oceanography at UC San Diego. So she is now involved with the whole institution, not just her own area of research. But her own particular research is really concerned with the Earth's magnetic field, and she's particularly interested in decadal to million-year-old variations in the geomagnetic field and how the changing structure of the geomagnetic field and events like geomagnetic reversals can inform scientists about processes in the Earth's deep interior. And just to tell you a little bit about Cathy before she starts her talk this evening, she was born in St Andrews, Scotland, which means she can actually understand what I say. But she was raised in Australia, and she holds a bachelor's and a master's degree from Australia. But she came to Scripps to do her PhD, and she basically never left. She held a postdoctoral research position, and since then she has held many research and professorial positions and is now, as I mentioned, a full professor. And she's also, as well as being a very distinguished scientist, she's also a distinguished administrator, and she has served as the head of Scripps Earth section in 2006 to 2009, as well as the director of the Cecil H. and Ida M. Green Institute of Geophysics and Planetary Physics. And she's a fellow of the American Geophysical Union and a member of the American Association for the Advancement of Science and of the Royal Astronomical Society, which awarded her its Prize Medal for Geomagnetism in Aeronomy. So please join me in welcoming Cathy for her presentation entitled Earth's Magnetic Field from Satellites to Reversals.
Thank you, Nigella, and hello, everybody. It's great to see you all here and to know that there's a lot of interest in the Earth's magnetic field. I think it's interesting, obviously, because I spent a lot of time working on it. And one of the most interesting things about it is that it changes with time. And what you see on my title slide here is actually a picture of maps of the magnetic field over the past 2,000 years. The front thing that looks like the head of the caterpillar here is actually the present-day magnetic field, and you can get some idea from this of how the strength of the magnetic field has been varying over the past 2,000 years. And I'm going to talk to you a little bit tonight about how we learn what we know about the magnetic field over long time scale variations, and why it's interesting, to me at least. So this is just a little bit of a coverage of what I'm going to talk about. I'm going to spend a little bit of time telling you why I think the magnetic field is important. Talk a little bit also about where it originates, which is from inside the Earth. Then I'll talk about measuring the field, how we know what we do know about the magnetic field, some of which comes from direct observations. Unfortunately, the direct observations don't go far enough back in time for us to learn everything we'd like to know about the magnetic field. So we're also going to talk about paleomagnetic observations or indirect observations of the magnetic field on millennial timescales and extending back as far as 2 million years, which is going to be the limit of where I'll go tonight. So first of all, to talk about the importance of the magnetic field, in here you see a couple of reasons why we should care about its existence. There is, of course, the very obvious thing that we use compasses for navigation, for orientation, and for location. And it's not just people who use the magnetic field for this purpose. It's also animals, birds, bacteria, and the animals have a couple of interesting things. They actually seem, in many cases, to be able to sense the presence of the magnetic field. And some animals have what's known as a compass capability. That is, they know which direction north is in. Others have what's known as a map concept for the magnetic field. That's a rather loose term of a map, I think, but they seem able to use the Earth's magnetic field lines as a mechanism for knowing exactly where they are in their local environment. So this is this pigeon here who is reminding you that it knows its way home by flying along the direction of the magnetic field. Homing pigeons use this. There are other animals like loggerhead turtles, Caribbean spiny lobsters, and various kinds of newts who actually have a mechanism for mapping the magnetic field, and they use that as a mechanism for navigating and finding where to go to nesting grounds and other things like that. Bacteria also, in some of the early work in discovering that animals were sensitive to magnetic field, came from people who looked at bacteria in sewage treatment plants, where they discovered that in the northern hemisphere they swim up along the magnetic field lines. In the southern hemisphere they swim in the opposite direction. Magnetic field is also important because of this rather nice artist impression which comes from NASA, which shows you the sun over here in this orangey piece, and coming from the sun there is the solar wind, which is a stream of charged particles, which then interacts with the Earth, which is pictured over here. What you see here are the magnetic field lines from the Earth, and they're being basically blown away by the stream from the solar wind. So what the Earth's magnetic field does do is it provides a buffer. This boundary here is known as the magnetopause. It prevents these particles that stream from the sun from coming directly into Earth and doing damage to people like us. When we have a magnetic storm, for example, this boundary is pushed inwards, and more of those particles are able to come in down through the polar lines in here, and we see those magnetic storms in the form of aurora and other phenomena. So that is actually one sense in which we are able to visualize the magnetic field. The magnetic field also protects us from cosmic radiation. This shield in here, which holds off the particles and deflects them around the Earth in what's known as the ring current, prevents these cosmic radiation particles from reaching us on Earth. Those are things that damage people. They're also, many of you may know, one of the reasons why manned space flight, when one leaves the Earth's magnetosphere, is actually a rather dangerous occupation for the people who would undertake it. So the other thing that this does is that if we didn't have this magnetosphere, as is true on some of the other planets, our atmosphere would be at risk for stripping by the solar wind. The particles that come through the solar wind would potentially blow away our atmosphere, and then we would no longer be here because we wouldn't have evolved in the way that we have. So these are a few things why we might be grateful for the presence of a magnetic field. The other thing you might think about, which is of course of some interest to me, is that there are many, many earth science applications for the Earth's magnetic field. Some of you may have heard my colleague Jeff Gee talk about some of those at the beginning of the summer in one of these lectures. It's used in plate tectonics, in magnetostratigraphy, which is basically the science of using the magnetic field for dating, and also as a mechanism for studying Earth's history and evolution. What does the magnetic field look like? Well, this is a little bit of a historical tour of how we've learned what we've known. This is William Gilbert. He was the physician to Queen Elizabeth I, and he was actually distinguished because he was one of the people who was very interested in measuring the Earth's magnetic field in the 1500s, 1600s. People have been measuring the magnetic field a lot longer than that, but he really was started to do something systematic and rather scientific. And he basically deduced from his observations and from making a little model of a piece of magnetic lodestone, which is basically a lump of iron oxide, which carries a permanent magnetization. He made a model of that, and then he deduced by doing experiments with compass needles around that the Earth itself is actually a magnet. So he basically said there's a magnetic field in the Earth, inside the Earth, rather than outside of the Earth. And it looks, by the way, a lot like what one would see from a regular bar magnet. It looks like a dipolar magnetic field. And if you look at the field lines, they look something like this. They come out in the southern hemisphere, they go around, they re-enter in the northern hemisphere. And one thing to note is that magnetic north is not quite the same as geographical north. So the magnetic pole is not in the same place as the geographic pole. And the other thing that's interesting about the magnetic field is that it actually changes with time. So you can see that in one of the features of the magnetic north not being aligned with geographic north is that if you use a compass to navigate, you won't ever get to the geographic pole if you follow it. You will instead follow a line, something like this line in here, the zero line here, which is a zero declination line. This is a measure of the deviation. The declination is a measure of the deviation of the magnetic north from true north. In California, it's positive, so magnetic north is, the compass points east of north, and you can see that in San Diego it's around 13 degrees. This is a contour map of the lines of declination in California. So Gilbert was measuring these things in around 1500 or 1600. People began to measure the magnetic field really in earnest when they started using the compass for navigation. And this shows you the spatial coverage, some early historical data. This is compiled by some colleagues from Zurich. And what you see here, every plus here is a measurement made by some ship that was going on a great voyage. And they made measurements of the deviation of magnetic north from true north. And each one of these is pluses shows what's going on. This is before 1590, and you see that the coverage is rather sparse. If you look after 1590, you see that there was lots of maritime trade opening up in here, and so people were making lots more measurements of the magnetic field, mostly of what we call the declination rather than the whole of the magnetic field vector, because the magnetic field is a vector property of the and so it not only has a direction, it also has a strength, and the declination just measures the horizontal direction of the magnetic field. So people made a lot of measurements. By 1700 already, this is a map. It's actually an example of one of the very early contour maps that was made by Edmund Halley of Halley's Comet fame. And he was interested in the Earth's magnetic field, and he made a contour map of the declination in the Atlantic Ocean. And what you see in here is this big fat line, which is less spidery than the others, is what they called at that time the line of no variation, which is where the declination is essentially zero. If you look at a compass there, you would be looking towards the North Pole. This line actually has moved westward with time, and it's now sitting somewhere over the Americas in the present day. And Halley actually knew already in 1700 that the magnetic field was not a static quantity, and he already knew also that the magnetic field came from inside the Earth. He actually knew pretty much what a lot of people know about the magnetic field today, even though he was looking at it in 1700, though he didn't know as much about the global properties. So to skip to the 20th century, when we measure the field today, we don't just use a compass. We use a magnetometer, which measures the whole vector of the magnetic field. It measures both the direction and the strength of the magnetic field, and we're able to map it pretty much all over the Earth. That's been done using a series of satellites. The first was the POGO, which stands for Polar Orbiting Geomagnetic Observatory in the late 1960s and early 1970s. This only measured the strength of the magnetic field, and people discovered that that wasn't enough. In 1979 and 80, there was MagSat, which measured the vector components of the field. And then there was a hiatus while people digested what they learned from MagSat and tried desperately to get more funding to go out and measure the magnetic field from a satellite. And since 1999, there has been a concerted effort, mostly by Europeans, to launch satellites. Some of these are in collaboration with NASA, and make a continuous mapping of the magnetic field over time. So these are 3 satellites that have been up since 1999. CHAMP, actually, it says since 2000. It actually re-entered the atmosphere a few months ago and was burned up. Ørsted is still working in a degraded mode. And the next satellite is planned by the European Space Agency, is actually a suite of several satellites that will called a swarm, which will map the magnetic field and will go up in June of 2012. So what does a satellite actually measure? What does it look like? This is a picture of the Ørsted satellite. This box here has a collection of instruments which run the satellite, do the housekeeping of various kinds of things. Then it has this huge long boom here, and right out on the end of this boom there are 2 instruments. This instrument here, this is a flux gate magnetometer of the kind that evolved from pioneering things by Vic Vacquier's father. And this thing on the lower part here is an Overhauser magnetometer. It measures the strength of the magnetic field. The flux gate measures the 3 components, so you can measure actually the direction of the field as well as the strength. Now you might wonder how you measure the direction of the field from a satellite that's spinning around above the Earth, and in order to do that you basically have to take a photograph of the stars and figure out which direction you're pointing. That's how one gets a direction of the magnetic field. This shows a picture of that satellite being launched, which was from Vandenberg Air Force Base just up the road. So these are the things that we use with satellites. The satellites aren't a complete solution to mapping the magnetic field, because when you launch a satellite, it goes into low Earth orbit at 300 or 400 kilometers altitude. It turns out that there are some magnetic fields between here and there, known as the ionosphere, basically a thermal place where the ionosphere contains ions. When ions move, you get electric currents which generate magnetic fields. And so the ionosphere basically heats on a daily cycle, and that results in small changes in the external part of the magnetic field. To separate those from the internal pieces and from the pieces due to the external field, we need to measure the field on the ground as well. That's done using observatories. The observatories have been mapping the magnetic field since about 1830, when Gauss, who basically was the first person to make a serious map of what the magnetic field looked like in 1830, he proposed, along with various other people at that time, von Humboldt and various French and British scientists, to put out a global network of magnetic observatories. And that's when people first started to measure the field strength around the world, as well as individual measurements of directions. So if you look at an observatory, you get a record that might look something like this. This is a measure of the horizontal, the north-pointing component of the magnetic field from College Station in Alaska. And this is actually a record of a magnetic storm. This is known as the Great Storm of 1989. It disrupted power throughout most of Quebec because of the changes in the magnetic field causing induction in power lines. When you get a big storm like this, it pushes in the magnetopores, that piece that I showed you at the beginning in the picture of the Earth. And what that does is to result in a very disturbed magnetic environment near the Earth, so that you can actually see aurora at low latitudes. And during this storm, there were actually aurora seen in Texas, whereas typically you have to go to Alaska to see them. It's not actually the biggest recorded storm. There was a larger one in 1859, but that was very difficult to record with the instruments in use at the time, so I haven't shown you that record because it doesn't look as pretty. But the one in 1859 apparently resulted in aurora all over the world. So when we take these observations, we use them to try and map how the magnetic field changes with time. And in a sense, a lot of what I do is making maps of the magnetic field and then looking at those maps and trying to figure out why they might be interesting. One of the things that we know is that because the magnetic field changes with time, the position of the north and south magnetic poles change with time as well. And it's actually the case that the north pole is the place where the magnetic field is vertical. The south magnetic pole is in the southern hemisphere, it's also vertical. But they're not antipodal, they're not 180 degrees apart. And the reason for that is because the magnetic field, even though it looks a lot like a bar magnet and a dipolar field, is not. It has some departures from that, and those are the interesting pieces, really. So what you see here is this is a map of the trajectory of the magnetic North Pole from 1945 up to 2000. You see that in 1945 it was at 74 degrees north. It's migrating northward at a fairly steady clip. If you look at the south magnetic pole, it was at 68 degrees south, and now it's gone as far north as 64 degrees south. So you don't have to go that far south in the southern hemisphere before the magnetic pole is north of you, which makes using a compass in Antarctica quite an interesting exercise. When we take the observations that we get of the magnetic field, we can convert them into basically a mathematical model of what the field structure looks like, and then we can look at what the magnetic field strength looks like over the surface of the Earth. And that's what you see here. This is a map of the strength of the field measured in nanoteslas. That's a very small unit. A Tesla, it's 10 to the minus 9 teslas. That's rather small. So what you see here is this interesting structure where you see these two lobes of strong field in the northern hemisphere, something that looks a little bit like that in the southern hemisphere, and then this funny blue patch in the South Atlantic, which is known as the South Atlantic magnetic anomaly. If the field were purely dipolar, we would not see this funny lobate structure in here. We would see something that only varied with around small circles of latitude. And what we see in here, so what we see here is a measure of the complexity of the magnetic field, how it departs from what you'd expect if you had a bar magnet at the center of the Earth. And you also see on here some white spots. These are part of why we care about the magnetic field. They are actually places where the Topex Poseidon satellite, which was a satellite that was measuring the topography of the ocean, so what the ocean height was, experienced what they call single event upsets. What that means is that some cosmic ray came in and damaged the electronics. It wasn't able to take a measurement there because of this interference. And the reason for that is because in this region, the magnetic field is much lower than it is elsewhere. And in fact, it's lower than what it would expect from a dipolar field of equivalent strength over the surface of the Earth. So this is a place in this region where you have to worry about having satellite components that are shielded from cosmic radiation. Otherwise, you will have difficulty in making measurements in low Earth orbit up there. On the right here, I'm showing you a difference in magnetic field strength as a percentage between observations made in 1980 and 2000 AD. So this is a 20-year difference in field strength for the magnetic field. And what you see is that there are some places where the changes are really quite large. If you look in this sort of around this South Atlantic region, you see that the field is decreasing quite rapidly. It seems to have gone down by about 10% in a 20-year period. So that might make you worry about whether the magnetic field is headed for its next reversal, which would be what happens when actually the poles flip and the magnetic field during a reversal decreases in field strength, and then it reverses its polarity, so the direction actually reverses. So a north pointing compass would point to the south instead of to the north, and then it grows back in the opposite polarity. We call that a polarity reversal. You also see in here there are places where the field is growing here, and so these are interesting things that are worth a lot of investigation. People spend a lot of time trying to document these things. You'll also note that there's a sort of hemispherical asymmetry in here, that all the decreasing seems to be going on this side, and all the increasing seems to be going on in this hemisphere. So that's another question that's of some interest. So there are a few questions based on these direct observations of the field that we'd like to be able to answer. We'd like to know what causes those flux lobes. I don't know if I said. We call these structures in here the flux lobes in the northern and southern hemisphere, this lobate structure in here. So we'd like to know what causes them. Are they always there? Are they a permanent feature of the field, or are they mobile, changing with time, sometimes not there? Is this hemispherical asymmetry in the rates of change something that we see as a permanent basis, or is that a temporary feature? We'd also like to know how quickly it can change. Will it reverse soon? How high could it go? Obviously, if we're interested in good satellite observations, good radio communications, stable power grids, we'd like to have a high magnetic field because that would shield us from the space weather that can interfere with those things. And then the other question is, how long can high values be sustained? And a thing that I'm going to talk about a little bit that's of some interest on very long time scales, it reaches into the origin of the magnetic field in the Earth's core, is does the field increase at the same rate as it decreases? So if we want to study long-term field variations, we could use direct measurements, but I've just told you they really only go back 400 years in global coverage, so that's not really going to work. We could use computer simulations in the Earth's core. They're hard because some of the parameters that one needs to work with require extremes of computing in terms of temporal and spatial resolution, so you need a lot of computing power, and you need to be much smarter than I am. So an alternative is to use archaeological artifacts and rocks as magnetometers. You might guess that rocks are rather low-grade magnetometers, but the process by which rocks are formed, in which they're either cooled down and acquire a thermal remnants, a permanent remnants, or deposited as sediments, allows one to preserve a record of the magnetic field. So it's a low-grade record, but it's one that has some useful information for us. Just to briefly go to where we think the magnetic field originates, I'm going to show you this slide, and then I'm going to show you a couple of these slides that do show actually how one can do a numerical simulation. It's not my numerical simulation, but one from Gary Glatzmeyer and Paul Roberts, both of whom work at another branch of the Institute of Geophysics and Planetary Physics at UCLA and UC Santa Cruz. So here's a picture of the Earth, the continents and oceans. This piece in here is basically made of silicate rocks, and we call this the mantle. The outer core is mainly made of iron. It's liquid. And the inner core is solid at high pressure. It's also mainly made of iron. The magnetic field is generated in this liquid outer core by thermal and compositional convection. What does that mean? Well, it means that the heat drives things to move around, which generates a self-sustaining magnetic field. The compositional piece comes because the core is not purely iron, but contains some light element, and that light element drives also the convection by essentially floating to the top, if you like. So here's a picture of the Geo Dynamo as simulated by Gary Glatzmeyer, and here's a picture of this simulation of the magnetic field actually undergoing a reversal. So what are we looking at here? These are the magnetic field lines. This goes out to about twice the radius of the Earth's core. And what you see in here are magnetic field lines which are coming up in the northern hemisphere and down in the southern hemisphere. And then you see this thing that looks like a bad ball of wool that the cat got hold of. And this picture over here, which I should allow you to see again perhaps now that you know what it is a picture of what happens when this simulation of a time-varying magnetic field, which is produced by writing down the physics equations that govern what's going on in there, and then letting them evolve over time, allows one to simulate actually the behavior in the Earth's core and what would go on at the Earth's surface, and actually produce a geomagnetic reversal. So you should just see this occurring over here. You see this simulation of this transition in the magnetic field. So The actual use of these numerical simulations has taught us an enormous amount about what goes on in terms of the physical processes in the Earth's core. Actually, it's been a mechanism for showing that there can be what's known as a self-sustaining dynamo there that will actually sustain the magnetic field over time. One of the things that we've been very heavily involved in here at Scripps in the magnetics group here is in trying to make observations and syntheses of the observations that can provide a sort of ground truth for these numerical simulations. And we do that by looking at very long-term properties of the magnetic field. So when we're interested in measuring the past field, we turn to paleomagnetism and archaeomagnetism. So what's the difference in here? Well, paleomagnetism means it's done on rocks, and archaeomagnetism means it's done on things that were made by people. And here's an idea of a sedimentary environment where sediment, already magnetized grains from rocks that have been basically eroded and then redeposited, are being deposited into a sediment. They preferentially align with the magnetic field as they're deposited. And then when the sediment consolidates, you have a record of the past magnetic field. It provides a good record of the direction and of relative variations in the magnetic field strength. So that as one moves down, takes a core in a sedimentary profile, or moves down a stratigraphic sediment and samples in time, one can get a more or less continuous record of what's going on with the magnetic field over time. And this is an example here. I think this doesn't show up very well, it's much too dark. But this basically is to show you that this is supposed to be a sediment core, and there are layers of sediment in here. And this would be the young piece at the top of the core, this would be the old piece at the bottom. And by sampling this core and knowing where it sat in the geographic coordinates, then we can actually make an observation of what the magnetic field direction looked like as a function of time, and what the field strength was doing as a function of time. The other kind of rock that gives us a record of the magnetic field, which is in some ways more reliable, is actually from igneous rocks. This is a picture of a lava flow on the Big Island of Hawaii from a few years ago. And this hot lava basically is heated above the point where the iron minerals lose their permanent magnetism. They then cool down and acquire a permanent magnetism that gives a record of what the magnetic field direction looked like, and also what the field strength looks like in some circumstances when one is able to reproduce the process in the laboratory. The bottom here you see a pot that has been fired. It turns out that fired pottery also contains magnetic minerals, and those are often also extremely useful for recovering the magnetic field strength with time. So if you go back in time and put these collections of observations, I should say they're not direct observations, they're indirect observations where we're using these materials as our magnetometers of the magnetic field together, then you can make a map like the one that I showed you that extends further back in time. And what I'm going to show you next is a map of what the magnetic field strength looks like over 3 time intervals. So this is one that you already saw. Well, you saw the first 20 years of this. This is an average of what the field strength looks like at the surface of the Earth, averaged over the past 400 years, from 1590 to 1990. And that's basically the full extent of the direct observational record. So you see this structure that we saw before where the color scale is not quite the same, for which I apologize, but that comes about because we have to compare it with others. But you see that there are these lobate structures in the northern and southern hemisphere. And then this piece that we saw in the most recent time that I called the South Atlantic anomaly, is situated, it's this broad low in magnetic field strength over the Atlantic Ocean that has evolved over the past 400 years, and you see in a slightly different place for the past 20 years. If you look in this next panel here, this is a picture of what you get if you look over the past 3,000 years. And it looks similar in some ways. You see some sense that maybe there might be some kind of flux lobe structure in here in the high latitudes, but it's not nearly as distinct as it is up here, and some sense of that perhaps in the low latitudes. But this structure in here doesn't really look at all like this. It doesn't suggest that this is a long-lived feature of the magnetic field. Turning to the bottom piece here, this is now an average over 7,000 years, and you see that things look different again. Perhaps the most obvious thing that you would see if you're tuned into the color scale here is that overall the field strength was lower when you average over 7,000 years than if you look over the past 400 years or even over the past 3,000 years. And I think I won't spend too much time on this one here. This is actually a measure, for those of you who've been staring at it wondering what it was, just a measure of what happens if you take away the dipolar structure and look at the piece that departs from that. And you see that, again, this is not something that is consistent over time, though the 3,000 and 7,000 year averages look a lot more like one another than the past few hundred years. So if we look at the strength of the dipole moment over the past 7,000 years, we see that that's this blue line in here. So this measures basically the strength of the magnetic field on millennial timescales. This is 5,000 BC to the present, basically. And these little lines in here are actually from some very recent observations as a mechanism for sort of tracking how well this is doing. What you see in here, and then in the lower part of this graph, you see actually the rate of change of the dipole strength, or the axial dipole strength over time. And this is perhaps the most interesting thing for those of us who might be worrying about whether the magnetic field is going to reverse next week. What you see in here is that it may not be a terribly reliable, or one should keep in mind, I should say, it's not as reliable as one would measure from direct observations. But if you look at this top graph, you see that, in fact, the dipole strength has been rather strong over the past 3,000 years, stronger than it was in the interval before that. And if you look at the derivative in here, what do you see? You see actually, well, this piece where the dipole moment is decreasing, and there have been suggestions that it's been decreasing steadily since 3,000 years ago. It's not actually the case that it's been decreasing steadily. It's been going up and down. There are large positive derivatives and negative derivatives in here. And if you look at the current negative derivative in here, it turns out that it's not anomalous by any measure when you compare it with what has gone on over the previous 7,000 years. So no worries, it's not going to reverse this week. I don't think. Unless there's something we've missed. Okay, so then the other question, next question I was asking was how high can the field go and how fast can it change, which might also be pertinent to whether it's going to reverse next week. So this is actually a picture that was compiled by my colleague Lisa Tokes, who has been doing archaeomagnetic work in the Levantine region. And she has been looking at material slags from copper mines, very old copper mines. And they have some measurements of magnetic field strength, which are shown in this lower picture here. And this black curve here shows a prediction from this magnetic field map or model that I showed you and its time variations. And then they see, lo and behold, in this region in here, they see some very rapid changes with time. And all of a sudden, instead of the scale here being one that ranges from sort of 60 to 100, there's an inset up here that's going all the way up to 250 or 300 zeta amp meter squared for the dipole moment. So that's a huge increase in the dipole moment. And the interesting thing is that they have rather tight age constraints on these data, and so they think it changed, they believe it happened very rapidly. So they see a change of about 70 microteslas in 100 years, and the question is that outrageous? And should we be worried about this if we saw something like this happening all of a sudden? Does this mean the field could grow very rapidly or decrease very rapidly? So if we look at this, we can look at this in terms of dB by dt. That's the rate of change of the magnetic field strength. It's about 700 nanoteslas per year. How does that compare with what we see in the modern field in the GUFM, which is this 400-year picture that I showed you? And in that time interval, we see something that's about 160 nanoteslas per year is the maximum. So this is a lot bigger, but not several orders of magnitude bigger, so maybe we don't need to worry about it too much. And it could be that it's something where we're looking at a very local change of behavior in the magnetic field. So I thought I'd show you a picture of how the magnetic field changes over a 3,000-year period. This is an animation. What you're looking at here again is the magnetic field strength. It looks different from what you saw before because this is 3,000 years ago. And what we're going to do is to look at how this evolves over time. So a couple of things to think about. Those lobate structures that I was talking about, you see something that looks a little bit like that in here, but it's in a different place. In the southern hemisphere, you see a bit of a blob. This South Atlantic anomaly isn't here if you go back 3,000 years, but there is another low in magnetic field strength that occurs here over the equatorial region, Central America, and then the Pacific. And so you can see how this evolves over time. And what you see here is something that's really quite dynamic. It changes a lot with time, but it basically preserves what we think of as the dipolar structure of the field, in the sense that it's high at high latitudes, low at low latitudes. But there are interesting features that evolve over time. And you see here, this is what we come down to in this, for some reason, has only gone to 1950 AD, but you see in here this evolution of the South Atlantic anomaly, which basically started in about 1850. There are other features that are like it earlier on, and they seem to be a function of what you see going on in the Earth's core over time. So this anomaly here doesn't seem to be something that's unusual. It's not fixed in place, but it does seem to be a feature of what you would see in the magnetic secular variation. I'm going to turn now to something on longer time scales, the million-year time scale. And when we look at the million-year time scale, we're again looking at paleomagnetic materials. There aren't any Archaea magnetic materials when we go back that far because people weren't firing pots that far back in time. So we're looking at now measures of field strength which come from igneous rocks. Those are things that have been fired and cooled down and acquired a permanent magnetization, from sediments. The archaeological artifacts go back to about 20,000 years ago is the oldest one. And this shows you a map of where we get some of those records. So there are 96,000 in total, and we've used them to try and make reconstruct a record of how the dipole moment, the strength of the dipole, varied for the past 2 million years. And we've made a model that we call PADM-2M, which stands for the paleomagnetic axial dipole moment for 2 million years. Oh, so I should say, we made two versions of this model. The first was actually a trial, these triangles and symbols of various kinds. The red triangles here are actually records that cover the past 2 million years from sediment. So they're the longest and best records in here, and the highest quality, we thought. The brown dots here are archaeomagnetic records, and they really only extend back to about 10,000 years before they drop off very severely in numbers. The other pieces are, the blue triangles are long records. The orange triangles are from things that only extend back to 50,000 years. And then there are some green ones which only cover the last reversal. So these are various codes for what's going on. But all in all, there are about close to 100,000 data. And we used them to reconstruct this record that you see here. There are two versions of this. One, the P, is the one from those long, high-quality records, which we used as initial trial on this. Then we made what we consider to be the best estimate of the dipole moment variations using all of the records, and that's this black curve in here. So a few things to note in here. These gray bars are the positions of geomagnetic reversals. What you see is that whenever you have a geomagnetic reversal, the dipole strength is very low. You also see that there are these, the shading in here is representing an uncertainty estimate on the dipole moment. What we will note is that the uncertainty is larger at older times. That's in large part because of problems with age constraints in matching the various records around the world. Another point to note is that, so this goes from the present day is at 0, I should have said. This is 1 million years ago. This is the Bruns-Matayama reversal boundary. This piece here is the Bruns, which is the current normal polarity epoch. of the magnetic field, so current polarity is normal and we're in it. This is the Matayama that goes all the way back to 2 million years. You might notice that there are other reversals in here, but it was named before those reversals were discovered. The other thing to note, it turns out that the average field strength is lower, significantly lower, by about 20% during the Matayama. And that's a sign that the field changes over very long time scales and has a lot of energy in the changes at very long time periods. Also, you might notice, if you're the kind of person who likes to look at these things, that when you look at the way this curve evolves, it's evolving this way from right to left because this is the youngest portion of the record. If you run your smoothing eye over this, you might notice that it appears that there are regions where the field increases very rapidly and then decays not consistently but rather slowly as it moves forward in time. And we found this an interesting thing because we wanted to investigate whether the field grows more rapidly than it decays. In order to do that, we smoothed this record. So this is the black is the thing that you just looked at in the previous slide. And then we said, what happens if we put a filter on here and we only look at things that occur? This is a frequency spectrum for those of you who care about these things. But basically what we said was we're only interested in variations that occur at longer than 40,000 year periods. And we also did this for other periods as well. When we do that, what you see in here is this pronounced effect where the field does indeed seem to grow more rapidly and then decay slowly. And we think that this is actually telling us something quite important about the processes that go on in the Earth's core, because it does seem that there may be a mechanism whereby one can build a magnetic instability that makes the field grow rather rapidly, and then it decays by something that looks more like a sort of what one would call a diffusive process, where it gradually fades away. And that's only a tendency, it's not a sort of a rigid physical law, I would say, because I think that the processes that are going on in the Earth's core are extremely complex. So this brings me to my summary. To remind you what we sort of saw in here. We showed CalS 3K.3 is this 3,000 year model that I showed you. It shows changes in the dipole amplitude and its structure with time. The flux lobes that we looked at seem to be present on the 3,000 year time period. They come and go, they're not fixed. Sometimes there are 3 in the northern hemisphere rather than 2. There are features like this South Atlantic anomaly, and these seem to recur in various locations over time. The dipole moment on the longer term, I said, I don't believe it's about to reverse. But when it does reverse, there are dipole moment lows, and there are differences in the average values of the dipole moment for the Bruns and Matayama polarity crons. The dipole moment grows more rapidly than it decays when one looks at a smoothed version where time period is longer than about 10,000 years. And this asymmetry that we see doesn't seem to be limited to the immediate vicinity of reversals, which I didn't show you, but is in fact true. So I'll finish with this slide here, which sort of shows you a picture of the geomagnetic Earth, like the one I showed you at the beginning. Here's the inner core, the outer core. There's motion convection going on in the outer core. Here are the dipole field lines. The external field is interacting with the internal field. And we measure all of these pieces, and we try and unravel what's going on in the very long time intervals. So I hope you've enjoyed this talk. I'll finish by saying some acknowledgements here. The work that I talked about is not just mine. It's actually also collaboration with a number of people. Monica Corta and Fabio Donadini are 2 postdocs who worked with me at various times on the millennial timescale modeling. Leah Ziegler is currently a student who's working on this million-year variations in the dipole moment. And Catherine Johnson and Lisa Tokes have also contributed a lot to this kind of work on the million-year timescales. And of course, we mustn't forget the people who sponsored it, which were basically National Science Foundation and NASA. Thank you. We've never seen it happen. So everything that we conclude about what happens when it reverses is that the field strength will drop to a very low value, probably somewhere, if I could, actually I could go back and show you this. If you look on this figure here, you see that the field strength is very low. It's around 20%, 10 to 20%. There's a lot of evidence that suggests it's very low. What that means is that we would, in fact, be exposed to more cosmic radiation, which would be a hazard. But, you know, the field has reversed in the past, and we're still here, as are all the other life forms on Earth. Maybe they evolved a little bit during the process. So I don't think that's a serious hazard. I would say the serious hazard for us as human beings is actually the interference with our electronic communications and our ability to continue with the comforts of life as we know it, that we've grown used to in those things. One of the things that I didn't say about the storm that I showed you from Quebec is that when that occurred, it actually occurred during the Cold War. And the general, and all the there was a lot of radio interference and things were not working at that time. So there was actually a belief that this might have been related to Russian activity, which set off something of a scare at the time. And then there were other people who believed that it was because we'd launched the space shuttle and the space shuttle had caused it. The question is, when was the last reversal? And the last reversal that we know of was at 0.78 million years. Those of you who are looking here will also notice, though, that there are other times here where the magnetic field strength has been rather low, and they correspond to what are known as excursions of the magnetic field, where it looks less like the structure you'd expect from a dipole. And you might expect some of the things that I just described about with the reduction in field strength when you look at what goes on in the South Atlantic where the field strength is low.
Why is there a magnetic field at all on Earth?
Okay, there's a magnetic, why did it start? Well, so the physics of what goes on in the Earth's core is basically that we have a conductive material that is moving, and it's acting in a way that allows an amplification of the magnetic field and a trade-off between the magnetic and kinetic energy in the core. So that generates basically a form of what we call a self-sustaining dynamo. So we have a source of energy that allows the material to flow around. The source of energy is basically thermal energy and compositional energy from this light element. The thermal energy is basically what we have left, if you like, from the energy when the Earth was formed, when the Earth was accreted, the material that makes the Earth. A lot of the compaction and gravitational energy in there was in the core, and that energy is what drives the magnetic field. Okay, so the question is about whether simulations allow us to look at the distribution of how often reversals happen. There are many simulations that have been done, and whether you get enough reversals to look in detail at the distribution or the statistics, how often they happen, depend on how realistic you make the simulations. If you make the simulations realistic, they become very time-consuming from a computational perspective. And then there are questions about whether one has the right well, there are always questions about whether one has the correct physical regime, but they become worse when one has low-resolution simulations. So people are able to make simulations where they reproduce things that look like what we see in the Earth, but there are some difficulties in those simulations, basically in getting the physics quite right. If one makes the viscosity of the core, which is very low, correct, then it turns out that one makes the day in the Earth very long. And so there's a trade-off between those two things. So the question is whether there's evidence that the core is expanding or shrinking or has always been the same mass. There is, as far as I know, no evidence that the core is expanding. There is a general belief that the size of the solid part of the inner core has been expanding over time, because what is happening is that it's basically solidifying as the Earth cools, And that's part of the process that's driving the magnetic field in the Earth's core, but not the whole core itself. The core itself differentiated from the rest of the Earth fairly early on in the Earth's history. I'm not quite sure I heard your question, but I believe you said, do we know why the south magnetic pole moves differently from the north magnetic pole? Yes. Okay. I think the answer to that is that it moves differently because the magnetic field is complicated. The approximation that would force the south magnetic pole to move in the same way as the north magnetic pole would be one that would make an oversimplified structure compared with what we see, and actually put some constraints on the physics of the fluid motion in the core that don't seem to be obeyed. One thing that I didn't mention was that if you look at some regions, and you may have seen this in the animation I showed, that if you look at how the magnetic field evolves with time, in some regions it appears to drift westward. Some features that you see seem to move to the west over time. And actually, for a long time, people used to think that that was the major feature of the secular variation. It turns out that if you look in more detail at these better maps and observations that we now have, there are some regions where the field is moving eastward in one hemisphere and westward in some part of the other hemisphere. And that's really a sign that the processes are not as one might have expected them to be equatorially symmetric, but they turns out that they're not.
What information do you derive from pottery?
Oh.
That you don't know the orientation of fire?
Okay. Well, the thing that you can derive from pottery is actually the ancient magnetic field strength by reproducing the firing, the acquisition of the magnetization in the laboratory, so you can get an absolute field strength. Sometimes you can get some idea of what the dip of the magnetic field, that's called the inclination as well, if you know which way was up and that it was fired on a horizontal surface. There are other artifact things like kilns and fireplaces where you can also get the direction of the field from archaeomagnetic things. Obviously, the measurements of the magnetic field are important to us as people. The thing that the magnetic field observations have done for us in the past have been to basically allow us to develop the theory of plate tectonics. The idea that the continents move over the surface of the Earth was really first discovered from making magnetic field observations in the distant past. And that's an important part of looking at the evolution of our planet. And it's also important in understanding how these things contribute to global change over time.
Well, on that note, I think I'd like to thank Dr. Constable for a really informative and interesting lecture, so please join me.